My name is Eric Page, and I'll be presenting on neighborhood consensus networks. So in this paper, the authors are trying to tackle the problem of finding reliable, dense correspondences between pairs of images, or in other words, pixel matching. More specifically, the authors wanted to be able to match pixels where there were repetitive patterns or very little texture to extract patterns. For example, here we have two images of a very, very repetitive building. It can be difficult to match features here. So the classical approach to pixel matching is to apply some sort of feature detection algorithm on an image and then finding the closest matching feature in the other image using nearest neighbor search. So each of the features output by SIFT is represented by a vector, and we can compute similarity scores in a number of different ways, such as Euclidean distance or cosine similarities, on and on and on. As you would expect, modern approaches replace the handcrafted feature detectors with data-driven learning methods. But these methods haven't blown away the competition as much as deep learning has in other areas, such as image recognition. So neighborhood consensus is a filtering step that uses neighboring features to help affirm or reject matches. In the example here, we can confirm that, that this pixel matches with this one because there are two other supporting pixels nearby. And this one can be rejected because there's nothing else, no other matches nearby supporting it. So the method can be broken apart into 5 different components we show here. Dense feature extraction and matching, neighborhood consensus network, soft mutual nearest neighbor filtering, extraction of correspondences, and weakly supervised training loss. So our first step is to take our two images and extract features from both images using a convolutional neural network. Specifically, the authors decided to use the ResNet 101 architecture. Then they compute the similarity score for every possible combination of points between the two images and put it into a 4D space where the I and j coordinates correspond to the row and column of the first image, and the k and l coordinates correspond to the row and column of the second image. They used cosine similarity to calculate the similarity score, shown here. It's pretty straightforward, just the dot product of the two features divided by their magnitudes. So every point in this 4D space will be a number between -1 and 1, representing how closely the features match, with where the higher the magnitude, the better the match. Negative values indicate inverse correlation. As a side note, I'd never seen this notation for the dot product before, so I figured I'd show this just for reference. So the 4D result of combining the two spaces may be difficult to imagine, so I created a graphic to help out. So the I and j coordinates here correspond to the row and column of the feature map for the first image. Likewise, k and l correspond to the row and column for the feature map of the second image. So we can input a pair of feature points we're interested in, and the correlation map will output a similarity score. So for example, if we choose the point here at 0, 0, and here we're at 1, 1, in the second image, we can see that they're a perfect match. They're both red, they're both frowny, so they have a similarity score of 1. Similarly, here at 1, 1, yellow smiley, and 0, 1, second image, they're both smileys, so another 1, perfect match. On the other hand, if we have a point here, 1, 0, it's a green smiley. Here, 0, 0, it's a green frowny. They're similar, but they're not a perfect match, so they're going to be somewhere between 0 and 1. For this, we'll just say it's 0.5. And if they're entirely different, so such as the red smiley here and the green happy face here, they are going to have a similarity score of 0 because they're nothing alike. So at this point, we have a massive number of potential matches in our 4D correlation map. Just as with the classical approaches, we want to be able to check each potential map or match and use the local information around the matched pixels to help affirm or reject it. Rather than use some hand-chosen rules, the authors wanted to make their method trainable, so they came up with the idea to use a 4D convolutional network. So by this point, I think we're all probably familiar with and comfortable visualizing 1D, 2D, and 3D convolutions, but 4D convolution can be a bit more abstract to visualize. Instead, we can view it mathematically, building up our understanding of lower dimensional convolutions. To get the result for a 1D convolution, we multiply each element of the kernel, W here, by a corresponding value in the input, F, and adding the result to the next calculation, which moves along in a single dimension. 2D convolution does the same thing, but once it's done in the first dimension, it increments along the second dimension and repeats. The same thing goes for 3D and 4D convolution. It's just an extension of the exact same algorithm. Now we want to make sure that the network produces the same output no matter what order the images are in. To do that, the authors apply the network twice, shown here. One network uses the original combination of images here, and the other uses the reverse over here. Notice that since the ResNet networks will produce the same output for a given image, we don't need to swap the images and create a brand new correlation map. We don't have to duplicate this entire thing over here, just backwards. Instead, we can just, if we just swap the ij coordinates of the correlation map with the kl coordinates, we'll get the same result as if we swap the images. So they feed these networks together and add them, so now it's order invariant. Soft mutual nearest neighbor filtering is used to constrain matches to filter out matches that are not mutual nearest neighbors. To help explain what that means, I created another graphic. Suppose we have feature John over here. He has the most in common in the second image with feature Jane. That doesn't necessarily mean that Jane has the most in common with John. Jane might have the most in common with Bob. So we want to filter these kinds of matches out. But if John has the most in common with Jane and vice versa, they're nearest neighbors, and we want to keep these matches. Here we define it more formally. If the feature with the smallest absolute difference from point CD is at the point AB in the first image, we define them to be nearest neighbors if the vice versa is also true. But this hard decision isn't differentiable and will prevent the system from being end-to-end trainable. Instead, the authors took a clever approach to both soften the decision and make it differentiable by using this equation, where the R's are ratios of the particular correlation score compared to the maximum possible correlation for one of the points. So RA scales a given correlation value, here's C, by the maximum observed correlation for the point KL in the second image. RB does the reverse and scales the value by the maximum observed correlation for the point IJ. And so in the case where IJ and KL are mutual nearest neighbors, both of these ratios will be equal to 1 and the correlation score will remain unchanged. And all other values will be scaled down based on how close to nearest neighbors they are. So to extracting correspondences from the feature map. So at this stage, our goal is to get hard feature matches so we can generate the actual point-to-point correspondences between the images. This step was actually fairly straightforward. They just used softmax. So yeah, they just use softmax to convert the values into probabilities. So at this stage, all of the hard work calculating and filtering correlation scores begins to pay off. Their method doesn't need the expensive manually annotated images, just sets of training pairs that are either matching, so they're positive pairs, they'll give a y value of 1, or they're not matching images, and they'll be considered negative images, give a y value of -1. So our loss value is just the sum of the averages here. This isn't a negative exponent, just FYI. Fooled me. And yeah, the sum of them multiplied by y. So we're essentially encouraging the system to find more and better matching features for positive pairs of images and penalizing it for if it finds matches between negative pairs of images. So to test their method, they conducted 2 experiments. One on category level matching, so matching points between objects of the same class, i.e. cats or bikes, and another on instance level matching or matching an image to a location, given a 3D model of the environment. So for the category level matching experiment, they used the proposal flow or PF Pascal dataset, which has over 1,000 images with 20 object categories. For the instance level matching experiment, they created their own dataset for training that they call the indoor venues dataset. They used Google Maps to find about 4,000 indoor image pairs taken at 89 different venues in 6 cities. And for testing, they used the indoor visual localization dataset, which has about 10,000 images made from panoramas and 300 more taken from smartphones at a different time, different lighting conditions. They did make some slight adjustments to their architecture depending on the experiment. So they used a relatively small resolution for category level matching. So they compensated by using 3 full layers with relatively large filters, so 5 by 5 by 5 by 5 filters. But for the instance level matching, the resolution was much higher. So they had to use some 4D pooling to bring it down to a workable resolution. And they only used 2 layers of smaller filters for their network. Both experiments initialized the feature detection part on ImageNet. I noticed that they didn't have to, but they just used this to, they didn't have to because their system is end-to-end trainable, but they did this just to help jumpstart it because it took so long to train. So for the first 5 epochs, they trained it with a fairly high learning rate, and they toned down the learning rate for the last 5 epochs. So the quantitative results are pretty convincing. They improved the state of the art on the PF Pascal dataset by just over 3%. Here PCK stands for percentage correct key points. So given a number of key points in an image, what percentage of them did they match correctly? And they did this without annotations. They had similar results with the indoor localization dataset. Here they're measuring the percentage of images correctly localized within a distance tolerance here. So the higher the tolerance, the better the accuracy, obviously. To do the localization they integrated their model into the pipeline of other localization methods like dense PE, shown here, dense PE stands for dense pose estimation, and the in-lock method that was originally proposed with the dataset. Okay, so one of the things the authors wanted to point out is that the PF Pascal dataset can be a little bit ambiguous. So take this pixel here. Is this pixel on the cat's face, or is it on its neck? For their method thought it was on the face, just on the very edge, while the ground truth says it's on the back of the cat. So it can be subjective depending on who annotated it. So, by the way, all the images that they show in the paper were picked at random, so they weren't cherry picking the best of the best. So these should be fairly representative of the overall results. So again, more great results. You can barely tell them apart. Like it's a little hovering off the backside here. generally pretty good. So here we can't see the bottom of the chair, so it looks like it may have mistaken these points for where the cross point, or where a crossbar intersects. Again, the data set can be a bit ambiguous. And more results, all looking good. Even for large numbers of points. Okay, so for the instance level experiments, notice that their method tends to spread out to find strong points, while the baseline tends to bunch up and find unreliable points in comparison. The author's method is also much more accurate, localizing within half a meter in this case, while the baseline was off by over 8 meters, and 45 degrees no less. So again, it spreads out the points, doesn't bunch them up. Baseline bunches them up, gets fairly unreliable results. Now, within a meter, almost 8 meters. So even in the cases where the baseline does manage to spread out points, it's still outperformed by the author's method. So here, it's off by less than 1 meter. Here, it's off by more than 4. So here we can see that their method is able to match pixels even when there's repetitive patterns. So there's a bunch of these similar looking columns here. It still manages to accurately find the points and accurately find the point correspondences between the images. Or the baseline, it doesn't do as good. Same thing here. Just look at the window frames. Bunch of columns, identical looking window frames, and it manages to do it nicely. And again, much better accuracy than the baseline. And that's it.